Okay, we have reached section 10.1, curves defined by parametric equations. So let's talk a little bit about what a parametric equation actually means. Up until now, we've been representing a graph by a single equation in two variables, typically y equals mx plus b type of a thing, or y equals x squared, something like that. Now what we're going to do is we're going to take situations where we have a third variable, and that variable, it could be anything. For the most part, we're going to use t, but that third variable basically becomes your independent variable. So if you take a look here, parametric equations, it says if f and g are continuous functions of t on an interval I, then the equations x equals f of t and y equals g of t are called parametric equations, and t is what is called the parameter for the parametric equations. Basically, you have to look at it like this. T now becomes your independent variable. Y and x both depend upon whatever you do with t. So x and y are now both dependent variables, and t is the independent variable. We've actually used parametric equations before, we just didn't necessarily call it that, but that's the general idea. Parametric equations can also be written in what is called vector form, where the first component of the function of x and the second component is the function of y. A vector has both direction and magnitude, much more heavily used in calculus 3 or multivariable calculus, but we'll use it just a small amount here. The notation for that looks like this, or at least the notation that we're going to use. There are several notations, but that is the most common one that we're going to use here. Basically, it looks like kind of like an ordered pair, except instead of parentheses, it is those angled brackets, and that indicates that you have a vector, and then the x component is f of t, the y component is g of t. Hopefully that makes sense just by looking at it. All right, so let's go ahead and see what this looks like. We're going to sketch a curve based upon parametric equations. So in order to sketch the curve, we're going to create this little table, or the table is created, we're just going to fill it in. Let's see what we get. So x is defined to be t squared minus 2t, and y is defined to be t plus 1. If I select different values of t, which as you can see we've got here on our chart, we're going to end up with what our x and y coordinates would look like based upon whatever t is. So when t is negative 2, if you plug negative 2 in for the if you plug negative 2 in for the x portion, right here, you would get negative 2 squared, which is 4, minus 2 times negative 2. So that's actually another 4, so 4 plus 4 is 8. And then if we were to continue that process, plugging negative 2 in for the y value, you would get negative 2 plus 1 here, which is going to give you negative 1. So I'll put that in red. And then if you just pretty much continue to fill out the chart, let's see our x values. So plugging in negative 1, you're going to get 1 plus 2, which is 3. Plugging in 0, we get 0. If you plug in 1, 1 minus 2 is negative 1. Plug in 2, you get 4 minus 4, that's 0. And if you plug in 3, you get 9 minus 6, which should be 3. So let's go ahead and finish out the y. By plugging in negative 1 into the y, you get 0. Plugging in 0 for the t value of y, you get 1. Plugging in 1, you get 2. Plugging in 2, you get 3. Plugging in 3, you get 4. That should make sense. It was a linear function, so negative 1, 0, 1, 2, 3, 4, increasing by 1 every time should make sense. All right, now let's take a look at what this thing looks like. What you can see is with the x value here, the x value produced some kind of a quadratic. The y value is some kind of a linear. Well, when you actually put those two things together through a parameter, let's see what it looks like. So in order to do this, do my best to try and fit this. I'm not going to be able to, so I'm going to have to scroll up and down, but that's okay. we're going to go ahead and label our graph based upon the chart. And it looks like x values are going to go from the smallest one we have is -1. The largest one we have is 8. So I'm going to make sure we can at least go out to 8. 1, 2, 3, 4, 5, 6, 7, 8. Fit a ninth one on there. I don't really have to go too far back on the negative part because it was only going out to -1 anyway. In the y, it looks like on our chart there, the smallest y value we have is -1. The largest one is 4, so we at least need to make sure we cover that. So there's -1, +1, 2, 3, 4. I'll go up to 5, even though we won't need it. All right, according to our chart, the first value I have, or the first ordered pair, when t is -2, x is 8, y is -1. So it's the point 8, -1. 8 is here, -1 is right there. So there is our first point. That is when t equals -2. Okay, let's go ahead and take a look at the next point, which is the point 30 when t is -1. Point 30, 1, 2, 3, 0, when t is -1. Our next point is 0, 1. That's when t is 0. 0, 1 right here. That's at t equals 0. I'm trying and write that without writing over top of too much there. Next one is when t is 1, I've got -1, 2. So -1, +2 is right here. And that's when t is 1. When t is 2, our point is 0, 3. 1, 2, 3 up here on the on the y-axis, excuse me. That's when t is 2. And then when t is 3, we are at the point 3, 4. 1, 2, 3, 1, 2, 3, 4, right about there. And that's when t is 3. So now if you just kind of connect that using a nice little smooth curve here, our function looks something like this. And if you listen carefully to what I just said, I said our function looks something like this. What we have here in standard x and y would not be a function. As a matter of fact, it would fail the vertical line test at several places, so it would definitely not be a function. However, in parametrics, this is a function because for every t value that we have, there is only one ordered pair associated with that specific t value. So it actually is a function. And it looks like this thing is parabolic. It just looks like it's a sideways parabola. And that's actually what it is. Eventually, we'll show how you can figure that part out. One of the most important things here in regards to this is direction matters when it's coming to parametrics. So you can see how I kind of labeled each one of those times. Time equals -2, -1, 0. So if you go in order, you can see the direction that this parametric function was created in. And as a matter of fact, what we tend to do is we put little arrows on here indicating the direction of travel or the direction that you are sketching this in. And that shows you the actual direction that the parametric was formed in. Now, obviously, this parametric is going to have multiple values more than what we have here. We just picked a specific number of them to start and stop with. Hopefully that makes sense as to how you would sketch a parametric equation. Again, direction is important, so the arrows tell you the direction. It usually just goes in order of t values from least to greatest. All right, let's move on. And it says we're going to sketch this curve. We're actually not going to sketch the curve, and you'll see why we're not going to sketch it in a second. By all means, you could go ahead and try to do so, but the values here do not lend themselves well to a sketch. But we are going to go ahead and figure out the values for this particular ordered pairs anyway. So it says that x of t is e to the 2t. y of t is e to the 2t minus 1, and t has to be less than or equal to 0. So they've kind of given us a domain here for our t values. Since t has to be less than or equal to 0, I'm going to put 0 over here. I can't go any past that, so that's going to kind of be my endpoint. And then I'm just going to pick whole numbers, and that's probably not the best option here considering we're dealing with exponentials, but it's not going to make it too difficult. So we'll just go -1, -2, -3, -4, and -5. Really, if I'm thinking about this, I probably should be using some kind of logarithmic values to give me nicer points to plot. But either way, it's not going to make anything extremely easy to figure it out. All right, so when we plug in -5, we are going to get for x e to the -10th power, or 1 over e to the 10th. For y, we are going to get e to the -10th power minus 1. For x, we are going to get e to the -8th power. Whoops, I don't know what happened there. And then for y, we're going to get e to the -8 minus 1. Hopefully you can see now why these are not going to be nice to graph. I mean, 1 over e to the 10th, not an easy value to graph. 1 over e to the 8th, again, not an easy value to graph. Plugging in -3, e to the -6, e to the -6 minus 1, e to the -4, e to the -4 minus 1, and then e to the -2 and e to the -2 minus 1. The only one that actually gives us a nice one is if we plug in 0, you would get e to the 0, which of course is 1. And if you plug in 0 for the y, you would get e to the 0, which is 1, minus 1 is 0. That one's the only one that gives us a nice point. All the other ones are just horrible points to try and plot. But anyway, that's how you would get the values. Those would be your ordered pairs. So it would go in order from t equals -5 to 0. If you were trying to sketch it, you would make sure you follow that specific path, whatever those ordered pairs look like. Okay, again, hopefully that makes sense as far as how it's going to be produced, how you're actually going to get the ordered pairs, how you're going to plot the points. Let's move on to example 2. Once again, it says we want to sketch this curve. More than likely, we are not going to sketch the curve. The important thing here is really the t values. So obviously we're dealing with trig, and we don't probably want to use, it says 0 to pi fourths, not including the 0, but including pi fourths. I really don't want to include like 0.1, 0.2. I want to use angle values that are going to make it relatively easy to figure something out. Now this is a horrible domain here, 0 to pi fourths. I don't know why I came up with this specific one or where I got this example from, but it's horrible because if I want to cut, let's say I've got 1, 2, 3, 4, 5. I got 6 boxes to fill in from 0 to pi fourths. I can't even include 0 because it's not included. I do know that pi fourths would be out here on the end. Now I have to figure out what kind of increments to go in. Well, I have to cut 6 boxes and cut pi fourths into 6 equal boxes. So I'm guessing I'd have to divide by 6, which is going to put everything in terms of 24ths. Yeah, this is pretty awful. But again, the idea just comes down to use trig values that make sense. And again, don't plug in for sine. You're not going to plug in 1, 2, 3, and so on. You're going to use things like pi fourths and pi halves and things like that that you can actually find the trig values on. Again, if I'm taking pi fourths and cutting into 6, I'm going to count by pi 24ths. So that would be the first one. Since I'm counting by pi 24ths, if I add a pi 24ths to pi 24ths, I would get 2 pi over 24, which reduces to pi over 12. Then 3 pi over 24, but 3 over 24 is an 8th, so that would be pi eighths. 4 pi over 24, geez, these all reduce. 4 over 24 is a 6, so that's pi sixth. At least that one's a value that we could actually know. And then 5 pi over 24, that does not reduce. And then 6 pi over 24 would be pi fourths. So that's the right increments. The only ones we're really going to know the values of easily is pi sixths and pi fourths. We could figure those out. But again, not really worth our time going through the actual ordered pairs there. You could certainly figure them out if you really wanted to, but not really worth it. I do not have any idea what this curve would look like. It'd be something we could play with at some point in time, but really not that important. Mostly there, it was just how you would increment everything if necessary. So again, don't worry about the fact that it says sketch the curve. All right, let's do one where we actually will sketch the curve. Example 3. And this will be our last example for this video, and then we'll come back with a second video, and that will be the lesson. So let's sketch this curve. So I've got x equals 3 plus 2t and y of t equals 5 minus 4t, both of which are linear. So it'll be interesting to see what this one forms. We're going to go from -1 to 2, including both. So I can start at -1 and finish at 2. Once again, I have 6 boxes. So if I'm going to take something which has a domain range of 3, cut it in 6 equal parts, I should be counting by halves, I would guess. So that should be -0.5, 0, 0.5, 1. Nope, that doesn't work out. Oh, it's because I'm including the -1. All right, well, let's just do this. Let's add a box. Why not? Just to make it work out. And then that would be 2. Yeah, if I didn't include one of the endpoints, this would have worked out nicer. Oh well, live and learn. Okay, so if we plug in -1 for x, we should get 3 minus 2, which is 1. Plugging -1 in for y, we should get 5 plus 4, which is 9. Let's see, if we plug in -0.5, that's going to be 3 minus 1, so that's 2. And 3 plus 2, I mean, sorry, 5 plus 2, which is 7. Now, really, if you're thinking about it, all this stuff should make sense. The x values, the x itself is linear with a slope of 2. So every unit should increase by 2, or every half unit should be increasing by 1. Might be easier just to think of it as every unit. So from -1 to 0, it should go up by 2, which should be 3. From 0 to 1, it should go up by 2, which should be 5. Of course, that means the inside one is 4 if we're just following the linear pattern. So then it would be 6, 7. Hopefully that makes sense. If it doesn't, plug them in. You'll see that you get the same numbers. And then the y values are decreasing by 4 for every 1 unit. So we went from 9 to 7, which makes sense because that's a half a unit. So it's decreasing by 2. So every one of these half units should decrease by 2. 5, 3, 1, -1, -3. So let's see what this looks like if we were to sketch it. How much negative space do I need here? X doesn't have any negatives. Y goes down to -3, so we should be good. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that's the highest y value, and we only need to go out to 7 on the x. 2, 3, 5, 6, 7. So let's see what this thing looks like. Got the 0.19 up here. Oops, that's supposed to be blue. There we go, 19, 27, 35. Okay, I am not doing a very good job here. 27, 35, there we go. 43. 5, 1. All right, there is definite human error here. 6, -1, and 7, -3. The way I've drawn this thing, it looks like it's supposed to be curved. It is not. It is actually supposed to be linear. I'm almost creating a line of best fit. But you know what the trick is? If you miss your dots when you're drawing your line, make your dots bigger. I don't know why I keep getting that little extension line there. Something's trying to tell me I need to be more careful, I guess. So there it is. It's supposed to be linear. All right, so that's how you come up with the values. That's how you come up with the points. That would be how you sketch the curve. Now, make sure that you know t started at -1, which is the 0.19, and then went down this way. So again, the arrows are important, going in that direction, showing us that. So this arrow up here was just the arrow for the line. I'm going to take that off of there. Arrows going in that direction. All right, that's enough for this video. We will come back with a second video. And in the second video, we're actually going to figure out how to algebraically do these. That video should be much shorter than this one and probably be a little bit more pleasing.